Well, hello crew. We haven't had videos for a chapter, but we're going to pick back up with them as we talk about rational functions. A rational function is simply a function that involves a fraction where x shows up in the denominator. So our first notes, we're going to make our 10.1a notes, which deal with power functions, specifically the definition of a power function and the graph of a power function. You're going to need your calculator for this, so if you don't have it with you, pause and grab it, and we'll be pausing the video several times so you can explore these graphs with your calculator. So here we go. We're going to start with the definition of a power function, right? And by definition, a power function has the form f of x or y equals k times x to the p. So our power is the x to the p. This looks a lot like the form of an exponential function, except what's different is in the power, x is in the base, whereas in an exponential function, x would be in the exponent. So here, k is our coefficient of our power, and p is the exponent in our power. So first of all, let's look at how we can identify whether or not a function is a power function, right? A power function, right, like this will have one term. So there won't be anything added or subtracted from it, and it will involve a power where x is in the base and x alone, and can be written in the form k times x to the p. So let's start with a. We have f of x equals 13 times the cubed root of x, and we know we can rewrite that cubed root. So if I rewrite this, I can write this as 13 times x to the 1/3, right? Yes, that is a power function where k is 13 and p is 1/3. And let's look at the next one. Here I have g of x equals 2 times x plus 5 to the 3rd. Looks a lot like a power function, except the base is not just x. There's something added to it. If we were to actually cube this x plus 5 and multiply those three x plus 5s together, right, we would not have a power function because there would be multiple terms. This is actually a polynomial function. Now let's go on and look at our next one. We have u of x. And if we rewrite this, we know that we can rewrite this square root as 25 over x cubed to the 1/2. If I distribute that exponent, then I get 25 to the 1/2 over x cubed to the 1/2, which would be x to the 3/2. Simplifying that, 25 to the 1/2 is the square root of 25, which is 5. And dividing by x to the 3/2 is the same thing as multiplying by x to the negative 3/2. So you can see that u of x, yes, right? So this would be yes. This is a polynomial function where k is 5 and p is negative 3/2. Looking at d here, right, looks a lot like a power function, except that x is in the exponent. So this would be no. This is an exponential function. So first objective is that you could look at definitions of functions and see if you can rewrite them in the form of k times x to the p. If you can, it's a power function. Identify that coefficient k and the exponent p. Now, let's look at the effective power p. And we're going to start by looking at some graphs. So we're going to let k equals 1, which means that we're going to look at equations that are of the form y equals 1 times x to the p, or just y equals x to the p. So the first one we're going to look at is the graph of y equals x to the 0, right? And we know that x to the 0, right, anything to the 0 is 1. So this is going to be a horizontal line that has crosses the y-axis at 1. If we look at the graph of y equals x to the 1, right, this is just y equals x, and we know that that is a diagonal line that passes through the point 0, 0, 1, 1, 2, 2, and so on. Now, neither of these functions are called power functions. They are technically power functions because they can be written in this form, but they have better names. Y equals x to the 0 is a constant function because it never changes. It's always 1, right? This is the same thing as y equals 1. And y equals x to the 1 is a linear function, right? Because its graph is always a line. So these have better names, and we would use them. Okay, now, let's look at power functions where we have positive integral powers. So that means our powers are integers, 1, 2, 3, -1, -2, -3, and so on, but they are positive. So this is where I want you to pause, and I want you to use your calculator to graph y equals x squared, y equals x to the 4th, y equals x to the 6th on the same axes, right? Identify how these graphs are the same, so you should be able to give me, 2 or 3 different things that are the same between those graphs, and then how they're different. And there's one important way that they're different. So if you will do that, pause, and you're going to answer these 2 questions on your Google form. And in addition, then do it for y equals x equals 3, y equals x to the 3rd, x to the 5th, and x to the 7th. And you'll notice that these powers are even, whereas these powers are odd, and you're going to see that that makes a critical difference. Maybe you're already anticipating it. So you're going to pause, graph those, make sure you sketch those graphs in your notes, answer these questions, and you're going to answer them in your Google form as well. Okay, welcome back. So hopefully you have a good idea of what's going on here. We're going to summarize this now, and we're going to look at several features that we're going to describe these graphs according to. So you already know about intercepts, that would be x and y intercepts, asymptotes, horizontal and vertical, domain, and range. Right? We're going to add this discussion of end behavior, which is simply how the function behaves, right, at its ends. It's its left and right end. Left end behavior is the same thing as the limit of our function as x approaches -infinity, and right end behavior is the same thing as the limit of f of x as x approaches positive infinity. So let's start by looking at our power functions where k is 1 and our exponent is an even integer. So if we look at the graph of all your power functions, right, all of those graphs look similar to y equals x squared, right? And examples of these would be y equals x squared, y equals x to the 4th, and y equals x to the 6th, and so on. So for each of these functions, the domain is -infinity to infinity, right? They extend forever, left and right. The range is 0 to infinity. They all pass through the origin and then are always positive, right? Which should make sense because if we're squaring, taking to the 4th or taking to the 6th, right, our result will never be negative. Our x-intercept is 0, our y-intercept is 0. There are no horizontal asymptotes. There are no vertical asymptotes, no asymptotes of any kind. Now, let's talk about our left end behavior, which is our limit, right, of our function as x approaches -infinity. If we take this graph and follow it to the left, it continues to go up, right? That limit is infinity, right? And sometimes we can refer to that left end behavior as up. If we look at the right end behavior, we're going to jump on our graph and follow it to the right. That would be the limit of our function as x approaches positive infinity, which we can see as infinity, right? Or again, that right end behavior is up. So sometimes when we describe end behavior, we would say that this graph has an end behavior that is up to the left, up to the right, right? And whenever our power is a positive, even integer, it has a shape similar to a parabola, though it may not always be a parabola. All right, let's go on and look at what's going on when we have an odd integer. So if our power is odd, so for example, right, if we had y equals x to the third, y equals x to the fifth, or so on, right, you probably saw when you graphed that your graphs all looked right, like this, had this S-shaped curve. That domain is also negative infinity to infinity. The range here is also negative infinity to infinity. The x and y intercepts are both 0. There are no horizontal or vertical asymptotes. Now our left end behavior is what this is doing to the left, which is going down, right? So our limit of f of x as x approaches negative infinity is negative infinity. So that is a down, right, left end behavior. If we look at the right side, follow this right, we're going up, and our limit of f of x as x approaches positive infinity is positive infinity. Our right end behavior is up. So those are graphs. We're going to fly those. So when I say positive odd integer, you should fly this graph, right, down to the left, up to the right, which again should make sense because to the left we have negative x's, cube a negative, it's negative, right? To the right we have positive x's, cube a positive, and it's positive. Now, for all of these graphs, what effect does increasing p have on the shape of the graph between -1 and 1? Hopefully what you noted is between -1 and 1, as p goes up, your graph gets shallower between -1 and 1. So if I were to do, right, so let's see, if this was the point 1, 1, and this were the point, that to plot, -1, -1, and I were to do, right, if this were the graph of y equals x cubed, right, this in red is y equals x cubed, if I were to overlay that with the graph of y equals x to the fifth, between -1, -1, and 1, -1, this graph would hug closer to the x-axis. Okay, beyond -1 and 1, the graph actually would become steeper. So if I were to follow this graph after this, this is going to climb faster, right? So it's still going to have that S shape, but it's going to hug closer to the x-axis when x is between -1 and 1, so a fraction smaller than 1 or a decimal, right, is going to be steeper, hug closer to the y-axis as x's are larger than 1. If you think about it, that should make sense. When x is bigger than 1, you cube it, it's going to get bigger than, it's going to get bigger when you take it to the fifth than you would to the third. What effect does increasing k have on these graphs? K is our, right, is our vertical dilation, so it's going to stretch the graph vertically, which is going to make it grow faster. So in general, it will be steeper. Okay. Now, let's look at what happens when we have negative integral powers. So like you did before, pause the video, right? Graph this, sketch those on your notes, answer these two questions, and then come back. Okay, so let's summarize what you saw. We're going to look at functions that are power functions, k times x to the p, where k is 1 and p is a negative odd integer. So examples, that would be like y equals x to the -1, y equals x to the -3, y equals x to the -5, and so on. So hopefully what you saw when you sketched this is these graphs all take a shape similar to this. So two pieces, right, where the domain would be from -infinity to 0 and then picking up with 0 to infinity. The range likewise, negative infinity to 0, and then 0 to positive infinity. There are no x-intercepts and there are no y-intercepts, but there is a horizontal asymptote at y equals 0, the x-axis, and a vertical asymptote at x equals 0, the y-axis. Now, let's talk about the left-end behavior. The left-end behavior would require me to come on the left side, on the left piece, and follow it to the left. Right? That would be my limit as x goes to negative infinity, which would be 0. Right? So my left-end behavior is 0. My right-end behavior would require jumping on the right side of my graph and following it to the right. It's approaching that horizontal asymptote, and the limit of this function as x goes to positive infinity is also 0. So my left and right end behavior are both 0 because on both ends it's approaching that horizontal asymptote. All right. Now let's look at what happens when our exponent is a negative even integer. So this would be like y equals x to the negative 2, y equals x to the negative 4, and so on. Right, so these graphs look a lot like our graphs where we have an odd exponent on the right side, right, pretty much the same. But what's different is on the left side, right, what would have been below the x-axis gets flipped above. And that should make sense, again, because when you have an even exponent, right, no matter what x is, the result is going to be positive. In these functions, our domain is negative infinity to 0, and then 0 to infinity. Right? Just like when we had a negative odd integer, our range is always 0 to infinity. These graphs are always above the x-axis, again, because of that even exponent. There are no x-intercepts, there are no y-intercepts, but again, we have a horizontal asymptote at y equals 0, the x-axis, and a vertical asymptote at x equals 0, the y-axis. The left-end behavior, right, at the left, this again is approaching our horizontal asymptote, so that left-end behavior is 0. To the right, again, we're approaching the horizontal asymptote, so the right-end behavior is also 0. For these graphs, what effect does increasing p have on the shape of the graph between negative 1 and 1? Well, if we were to take, right, a point, and we'll call that 1, 1 here, or a point here, and that would be negative 1, 1. If our input is a fraction less than 1, so for example, if we took 1/2 and we raised it to the negative second, the negative would flip that and we get 2 to the second, which is 4. But if we were to take 1/2 and raise it to the negative 4, that would be 2 to the 4th, which is 16. So what happens is that if this is my graph of x to the negative second, then my graph of x to the negative 4th would grow faster. So it would actually be steeper inside and then would be shallower to the outside. Right, so it would have that. What effect would k have, again, on these graphs? And again, it would stretch the graph vertically. Right, we have that outside multiplication by k, and so that's a vertical dilation. All right, now what do we do when we have fractional exponents? So go back and graph, right? You're going to pause again, graph these 3 functions on your calculator, answer these questions on your Google form, and then come back. All right, so let's summarize this. So here we're looking at where we have functions, right, again, that are power functions with k1, but this time our exponent is a positive fraction with an even denominator. So this would be like y equals x to the 1/2, right, which is the square root of x, or y equals x to the 1/4, right, which would be the fourth root of x. These graphs all have this shape that starts at the origin, because you can't have a negative under an even root, and just has one arm to it. The domain of these are from 0 to infinity. The range also from 0 to infinity. Passes through the point 0, 0, so that's both the x and y intercept. There are no asymptotes, no horizontal or vertical asymptotes. The left-hand behavior, right, I can't find the limit as x goes to negative infinity, but at its left end, this graph, right, approaches, at its left end, this lands at 0, so its left end behavior is 0. The right end behavior is what it's doing on the right, and on the right end it continues to climb, so its right end behavior is infinity. Yeah, we'll talk about this in class, this left end behavior here. All right, let's look at the next one. This is where we have a positive fraction with an odd denominator. So this would be like y equals x to the 1/3, or y equals x to the 1/5. So this would be like the cubed root of x or the 5th root of x. What's different with these functions is that we can have negative x's because we can find the cubed root of a negative number. For example, the cubed root of -8 is -2. So to the right, these graphs look very much like x with a x to the 1/2, but there is a piece to the left which comes under the x-axis. So our domain is -infinity to infinity. Our range is also -infinity to infinity. Our x and y intercepts are both 0 because this graph passes through the origin. There are no asymptotes. And the left end behavior, right, would be, as we follow this to the left, would be our limit as x goes to -infinity, which is -infinity. So it goes down, right, slowly, but it continues to go down. Our right end behavior would be our limit as x goes to +infinity, which is +infinity, right, taking this to the left. So its right end behavior is up, continuing to climb, though slower and slower. Right? So for the graphs above, right, what effect does increasing p have on the shape of the graph? Well, if we call this 1, 1, and this here -1, -1, when we take fractions and take their cubed root, they're going to get, so like if I were to take the cubed root of 1/8, that would be 1/2, which is going to be bigger than 1/8. So what happens then is that in between, these actually go above, right? But after 1, they go below. Okay? So here they get steeper. Here it gets shallower. Okay, again, K, vertical stretch. Okay, and I think that takes care of it for us. So we'll fly these graphs tomorrow in class. You've got Google form to fill out, and we'll talk more about this tomorrow.